So reflections, as you can see, right, we've got a reflection here of this mountain, and there is this line of reflection where we can see where all the points would line up. They're mirror images of the pre-image, and we get isometries, and what that means is just that the pre-image and image are going to be congruent. A line reflection. So the mirror line, the place where you would fold the paper and you'd see all the points lining up, that's the line of reflection, and the image is a flip of that pre-image. So reflections can occur over any line that you want. For our purposes, we're going to be talking about reflections over the x-axis, the y-axis, over the line y equals x, which if you recall, that line looks like this. There are reflections over the line y equals negative x, that looks like that, so you can reflect over those lines. And we're also going to look at any other horizontal line or any other vertical line in the plane. That's where the reflections we're going to look at, but you can have reflections anywhere. So here's an x-axis one, so you've got that example on there. Mirror images where x-axis is that line of reflection. The formula you would use to make that transformation is you start with each xy in your pre-image, and then the x stays the same, but the y gets negated. It becomes negative. So 4, 2 became 4, negative 2. So you can figure out what all the points are. You may have learned with counting boxes, but I think we want to get to this stage where we're actually seeing the transformation of the points. The y-axis, that's where we're going this way. The y-axis is that fold line, and that transformation is you take each xy that's in the pre-image, the x gets negated, and the y stays the same. And that kind of makes sense, right? If you're going 2, 2, so now you have to go negative 2 and then up. So the x value will be negated. This y equals x, that's going this way, right? There's y equals x. It's a little bit harder to see. You have to, again, kind of see that the paper being folded along that red line, y equals x. That mapping is xy goes to yx. So we're switching the coordinates around. So negative 4, 2 became 2, negative 4. Switch the coordinates around. Okay. So y equals negative x, that's this line. So again, they're a little harder to see, but you have to kind of picture the page being folded. That mapping, xy, now we turn them around just like we did for y equals x, except they get negated as well. So we have these different kinds of mappings here. So a lot of different mappings. Now when you're working with any other vertical or horizontal line, my advice, this is a count boxes exercise. I think that's the easiest way to handle them. So if I've got, here's my pre-image. So let's say I want to find the mapping of B. Here's my line of reflection. I notice B is 1 point away from it to the left. So I look 1 point away to the right, and then I found my B prime. Same thing if you have a horizontal line of reflection. I would do the same thing. If this one's one way and this one's one in the other direction, I just think it's the easiest way to kind of deal with them. There are other ways. I don't know if it's supposed to be in the timeline, so. All right, so here is a summary of them, and I have them on your page here. You kind of have a highlighter. These are good things to highlight or circle it with, little arrows and stars. It's the kind of the big idea, the big thing you need to know to kind of do the question. So the last one I'm going to talk about here, point reflection. A point reflection, that's an interesting little thing here. It's more of a rotation than a reflection. So basically what happens, you have a point, and you're basically reflecting around this point. So A here, A prime here. What's happening is there's another point directly opposite, kind of in that same distance away, so that this is the midpoint. So the same distance here, keep going on that straight line, same distance. Here's this one, go to that center point, now go the same distance here, that's where that point's going to go. This distance to your center point, keep going until you've gone the same distance. And that's where you find these other points. But for me, I really see it as a rotation, 180 degrees, and we're going to talk more about rotation. But look at it, it's upside down now. So it's like you rotated that thing around 180. So a point reflection is the same as a rotating at 180 degrees. And I'm on the back, so hopefully you're all with me on the back. Right, talking about point reflections? Okay, so how do these work? Let's look at these points here. 1, 4 became negative 1, negative 4. 1, 2 became negative 1, negative 2. the mapping is xy goes to negative x, negative y. So the points stay in the same locations, we're just going to take the opposite values, the negative values, which means, if it's negative, you make positive, so other value. And so rather than a U-try, let's just use this as an example because there's not a lot of them on here. So graph your pre-image here of ABC. I'm going to try. I tend to mess these up on this thing just because it's hard for me to count it. So if I make a mistake, let me know. So here is my pre-image. We got our pre-images. So this one little question is really asking you to do a lot of different things. Reflect that figure over the x-axis, reflect it over the y-axis, over the line x equals -2, and over the line y equals -1. So let's start with the x-axis. So let's see, I want my A prime, my B prime, my C prime. I do want to see these points. I do want to see the new transformed xy coordinates. Don't just run to the graph. So write the rules down for these. So how does that work? If you have a reflection over the x-axis, each xy pair, the x stays the same, but the y becomes negative. So let's see, if this is 2, 4, the x stays the same, but the y becomes negative. If this is 6, 3, the x stays the same, y becomes -3, and that becomes 3, -2. And now I can go ahead and graph that thing. So x-axis, so I'm going 1, 2, 1, 2, 3, 4. That's A prime. And then 6 here, so 1, 2, 3. So like a check would be, does it look like if you fold it along the x-axis, are these points all going to line up? So a lot of kind of imagining what it could look like as a check. Now the y-axis, that rule was each xy transforms to, the x becomes negative, but the y stays the same. So I'm still calling A prime, B prime, C prime because I'm not transforming the last image, so it's a little confusing. Because let's see, the x's all become negative, but the y's stay the same. So I'm looking at the original points. I'm looking up here and then I'm looking back down. I'm looking over here, and that's how I'm making, this one negative and that one not. Colors. These colors have not been showing up that great on here, so let's see what happens here. -2. And it should look like I'm going over the y-axis. That's not a great color. These are very good, these colors. A little better. Not really. All right. -6. So there's my reflection over the y-axis. Now when I'm working with the line x equals -2, so what I would do is kind of sketch this line in. Remember what this looks like from algebra. This is a straight up and down line at x equals -2. So I'm going to kind of sketch that guy in here. And then I say, okay, I want the image of this A. Well, how far away is A from my line of reflection? It's 1, 2, 3, 4 points away. So now I'm going to count 1, 2, 3, 4 in the other direction. And there's the A prime that goes with that. This B is how far away? Well, 1, 2, 3, 4, 5, 6, 8 of them. So keep going. 1, 2, 3, 4, 5, 6, 7. I think it's here. I'm kind of landing right. This one is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then for y, even already up. So let's see, y equals -1. What does that look like? That's that horizontal line over at y equals -1. Do the same thing. So A is how far away? Well, that's 4. One more is 5. 1, 2, 3, 4, 5. B is also being on this one row graph. Questions? Anybody? Yes? X equals -2. I drew an x equals -2 here. And I basically counted how far away is A from there? It was 1, 2, 3, 4 away. So then your A prime is going to be 1, 2, 3, 4 away over here. So you're just kind of making it equal distance from it. Yeah, and the same kind of idea of the y equals -1. Yes, sir? What? Which one? From here to here? I did count from how far was this B from the line that I'm interested in, whatever that distant was, I went the same distance here. When I was going from this line, I just said how far away is B, it was 4 away, counted 4 boxes after that B. And then we can use the formulas for the other ones. Alright? The y equals x, again, I like sketching what I'm doing. It's always nice. This one I'm looking at y equals x. So when I'm what's the rule for y equals x? They swap, right? The x's and the y swap. So when I do my a prime, my b prime, and my c prime, they are going to swap. I guess I should back the original one. So that's our pre-image. They should be primes. Those aren't primes, those are just regulars. Okay, so that's the pre-image. And so this one now I'm just going to swap them around. So I'm looking at this 4, -4, and I'm just swapping the values. I'm looking at this guy, swapping the values. X becomes y and y becomes x. And then we graph that down. -4. This is fun. So get the full one left diagonal. These should go one right on top of the other. To do y equals -x, that's going this way. That's this line. So when y equals -x, what is that transformation? Xy becomes what? What is it? Same thing, right? Except they're negative. So you do swap them, just like we did before, but now they're both negative. So the easy way is, since I've already done this, I can just make these negative. So each x and y is going to be the opposite of what I see here. So this one is overlapping. So what's happening? Remember, this is the line we're reflecting over for that one. So they're going to line right over each other. It is possible that if your original figure kind of crosses this line, they could cross over each other. There can be overlap. So don't worry. If that happens, that can be normal. And then, what's going on with this guy? This is the point reflection. And just look at the language. It says graph the reflection of ABC in the origin. And that means a point reflection. And that rule was, what was that rule? Right? They're the same, but they're negative. So quickly go ahead and graph this guy. You can do this, right? -2. I can't. 1, 2, 6. Make sure you are putting these points on. I mean, this is important. If you want to see these inch points. So make them negative, so I'm looking at these, becomes 2 negative 6, becomes 2 negative 1, becomes negative 3 negative 1. Just making all these values opposite. 2 negative 6, 2 negative 1, and negative 3. And it should be upside down because these are rotations of 180 degrees. I may have missed that, that's all. But that's what it should look like. Questions at all? You just kind of follow these mapping rules and you should get there. Okay? We're ready for the next thing? That's the whole first paper done. Yeah, that's the whole first paper. That's it. That's it. Now rotations. Rotations are, I got my Mickey's Fun Wheel from California Adventure here, so rotating around in California there. So a rotation, you're transforming the figure by rotating it around a fixed point. That's my center of rotation right here. And so if you were to look at one point, so here's A, and I draw it to the center of rotation. If I find the matching point in the image and draw that to the center point, that would be the angle of rotation. That's how I'm figuring out that this is a 90-degree rotation. And they are isometries as well. This will be congruent to that. They should be congruent. Now this next little bit here, this was something that I know was confusing to me when I first learned how to do this. First of all, do we know how to read a clock like the one on the back wall? We know how to read that clock? We do? We're only saying that because we never see that, right? Everything's digital. So like a clock, you know, you have a clock. What's clockwise? Like this way, right? That's clockwise. Isn't it? That's how a clock, the hands go. So counterclockwise is the opposite way the hands go. So that's counterclockwise. Okay, we know that that's good. Now here's what's a little bit confusing. It's natural for us to think that this is the correct direction, right? Correct. When we talk about angles of rotation, this is clockwise is not correct. Counterclockwise is normal. That's the positive direction. So going this way, that's positive degrees. Going clockwise, which we want that to be normal, it's not. That's the negative direction. Thanks, Matt. Thanks a lot. Right? Well, you know, it's kind of maybe a little bit not intuitive. But that's how it works. So if I'm looking at my kitty here, and that's my pre-image. I didn't make up the rules. I didn't make them up. So this guy's the pre-image. So this image here, that's a 45-degree rotation. Now how do I know that? Let's say it looks like around here is my point of rotation. If I start from this whisker on the pre-image, and I go to the same whisker on the actual image, you know, this is 45 degrees. And since I went in this direction, it's positive 45 degrees. If I would have gone 45 that way, that would be negative. Now, if I put my kitty over here, I rotated him 90 degrees, this whisker to this whisker, more or less, right? 90 degrees. This is a negative rotation. That's negative 90. Now, there's another way I could get this image. I could have taken this kitty and gone around, a positive 270 degrees. It's equivalent. Going negative 90 and going positive 270, that's equivalent. Yeah. So be real careful not to mess that up. We want to keep it that way. When you get into trigonometry for reals, that's the same kind of rotation. You're going to see positive goes this way, negative is the other way. Okay, so you can rotate a figure any number of degrees, but what we're going to be worried about, 90, 180, 270, or right, negative 90 if you want to think about it that way. Here's the rules. These are the mappings. So a 90-degree rotation, negative y, the xy becomes negative yx. Turn them, first thing becomes negative. 180, you don't turn them, but they're both negative. And this should look a little familiar, right? Looking at the same as that's the same as our point reflection. It's the same as a 180 rotation. And at 270, you do turn them, but the second one is negative. The y value, the new y value. And yes, you have to know this. This is not anything on the formula sheet, so we are going to have to know this. We'll think about it a little bit later how we might remember it. So anyway, here is an example in the middle of page 1. Yeah. So what happens here? Let's put our quadrilateral on here. So go ahead and grab this if you haven't. 1, 2, 3, 1. Getting our free image on there. We're going to be rotating the quadrilateral 270 degrees about the origin. So this thing, around this, we're always going to use this as our point of rotation, the origin. You can use any point, we're just using this one. And it's going to rotate around. So how do we do it? So first of all, we kind of have to remember the mapping for that. So you start with your XY pair, and for a 270 rotation, you swap them, and the second, or the new y value becomes negative. So here's the original values. So let's see. Swap them, and the new value over at the y is negative. Swap them, and the y value is negative, or opposite, I should say. Swap them, and that 5 now is negative. Swap them, and that is negative. So just so happens, since these were all positive, these came all negative. If you had a negative number, obviously it's taking the opposite, it would turn positive. So now we can graph those guys. So 1, negative 3, 1, negative 5, negative 5, negative 1, negative. So it should look like it turned 3/4 of the way around. About the origin. And then we're on the land of U-tries now, but are there questions? It's really just knowing what the mappings are and making those little transformations and then graphing. So, can you try these guys? I'm told B, it looks cool. That's what they said last class. This is what I got for the first one. Does it look right? We're not done with the first one yet? This is what I got, so you can check that. I'm just going to kind of scroll through with the answer key, and then you can work at your own pace. So don't worry if you're not keeping up. That's right. I don't know if anybody got through B. It's kind of awesome, B. What? And then I want to talk about this guy, too, so we will. So. The important thing when you're working these is make sure that if it's a 90-degree rotation, you wrote out this rule. If it's a 180-degree rotation, you wrote out this rule. 270, write out the rules so that you can make the transformations on the points. This one's kind of crazy because it's all on one place. Now this one, see, a lot of people said 45 degrees. It's not 45 degrees. So in the beginning, when I talked about the angle of rotation, I said, like, so you start at your point, your center point, which is right here, and pick any point you want. So I'm going to pick this point. And it's this kind of figure, right? This little piece here that gets rotated. So look on another one of these guys here, and I'm going to go in the positive direction. This is kind of that matching point. So it would be here. What does that look like approximately? You have to estimate, right? I'm not looking for a protractor or anything. What do you think? 90 degrees. So that's how you figure out what is the degree of rotation. Where the matching point would be from the center, what is the angle? Does that make sense? Yeah. Sure it does. Okay. Last little bit, we're on the back of the page here. Back of the page. Dilation. So a dilation is a transformation that produces an image that is the same shape but a different size. When things have the same shape but different size, we say they are similar. So instead of getting congruent figures like we did with all the other ones, you'll get a similar figure. So I got my eye here because I dilated, so you can kind of remember getting bigger, smaller. So dilations are enlargements or reductions, and we sometimes see other words. Stretch for making something bigger, shrink, or even compress for making things smaller. So that's what this picture is. Dilations of this circular shape here. They're not isometries. They are similar, but not congruent. So what else can we say? The center of dilation is illustrated below. So there is a center of dilation. For us, we're always going to use the origin for our center of dilation, but it doesn't have to be. And so here we have this tiger, and here it is dilated larger, enlarged. The scale factor is what you apply to the pre-image to create your image. So on this original image, we applied a scale factor. The scale factor then is multiplied. It's a multiplier on the pre-image. Not really sure how much bigger this thing is. 2 times, 3 times, I'm not sure. So let's say it's 2 times bigger. Then you would take every point here, multiply by 2, you get the points over there. Multiply, multiply, multiply. So if you know that you have pre-image and an image, you can actually find the scale factor. I'm just making up points here. If this was 4, 10, and this one was 8, 20 in the matching place, how would you find the scale factor? Divide. 8 divided by 4, 20 divided by 10. You should get the same number. So this one, scale factor 2. So if you have a scale factor that is bigger than 1, you're going to get something bigger. And if your scale factor has a magnitude between 0 and 1, then it's going to be smaller, because what numbers are between 0 and 1? 1/2, 3/4, 7/8. So when you apply that scale factor, you get a smaller figure. So if this was the original, and that was the dilation, that would be a scale factor of 1/2. That's smaller. All right. So for us, again, we're using that origin as the center of dilation, and there's no real magic here. It's pretty easy. For each point, just multiply the x and multiply the y by your scale factor k. That's all. So for this example here, we're going to create, again on the back, if you know where I am, example A. Let's graph our pre-image. A of -2, -2, B of 1, -1, and C of 0, 2. So that's my pre-image. Reading the question, it says we want to dilate with a scale factor of 2. So to create my transformed points, I'm going to multiply the x's by 2 and the y's by 2. So -2, -2 becomes -4, -4. This guy becomes 2, -2. This guy becomes 0, 4. So then I can go and graph those. So -4, 1, 2, 3, 4, 1, 2, 3, 4. -2, -2. 1, 2, 3, 4. This one, this one, this one. Similar shape. One is bigger than the other. We enlarge that triangle. Is it? It is. Okay, next one. Let's look at the next one. This one, a pentagon. Oh, good. 5 points. All right, so I'm going to dilate a pentagon by a scale factor of 1/3. Really? All right, let's get the pre-image on there. So let's see. There's A. Just plotting my pre-image points. You should be doing that too. Those of you doing nothing, get busy. 6, -2. So there is my pre-image original pentagon. So let's figure out what the prime values are here. Have to multiply x's and y's by 1/3. So 0 times 1, that's easy, right? 0 times anything, 0. 3 and 3, so 3 times 1/3 is 1. 6 times 1/3 is 2. 3 times 1/3 is 1. I'm really basically just dividing by 3. Oh, look at this one. Not a nice number divisible by 3, so I guess I'll just leave it like -2/3. Don't make it a decimal or anything, just that's fine, -2/3. 3 over 3 is 1, and then -1. Right? Just dividing all those numbers by 3. This one we get a little teeny tiny guy. So here is A prime. It's the same as A. 1, 1, 1, 1, 2, 1. Prime. It's so tiny. 1, 2. For -2/3, I'm just going to do my best. It's around here. We'll estimate for where that is. And then 1, -1. should be, like if you did the points right, it should be a nice similar figure to it. It's 1/3 size. No? Are there any questions? It's not too tough. So the tricky thing here is knowing all the different mappings here. So go ahead and try these ones. These should not take too long here. You're just doing a dilation in the first one. Second one, you're figuring out a scale factor. For C, the copy is very hard to figure out what the coordinates are. So if you look up on the board for C, I did write out what the different coordinates are because this did not copy well the grids. So I'll leave that up there for you to look at. So go ahead, try these U tries. I'll flip through with answers just so I have it on record. But I'll flip that. Yeah, 15 over 6 because 6 times 15. So 15 I divide by 3. And I get 5/2. So whichever point you use, the 4, how did I get to a 10? Or the 6, how did I get to a 15? That's how you figure out scale factor. This guy, same kind of thing. If you just pick 2 points here, what's the scale factor? These are all the points. So -2 went to -4. -1 went to 2. 2 went to 4. What did I multiply by? 2. So your K is 2. Alrighty. I just look it up in your notes, right? We want to make sure we have this one right, because if this paper's wrong, everything's going to be wrong. Just check my work too here. Like I can kind of remember this. This one makes sense. Over the x-axis, x stays the same, y changes. Over the y-axis, y stays the same, the x changes. Turn them to look like y equals x. I can kind of remember these. I remember that point reflections and 180-degree rotations are the same. So that's good. For me, the kind of hard ones to remember are these 3. And you really need to come up with a good way to remember them. I can tell you what I use. It may or may not be helpful for you. This is how I remember which one's which.
Why
for the
K?
90 and the 270 and this one too. I'm at 180.
What is dilations be?
What? Dilations easy.
Why is there a star?
There shouldn't be. It should be on the other one. Okay, so what I do to remember them is I think of a coordinate plane, right? So let's say my original figure was in the quadrant 1. Right? If it was in quadrant 1 and I rotated it 90 degrees, it would probably be in quadrant 2. And then I think of quadrant 2. The x value is negative and the y value is positive. So here's a negative and here's a positive. If I went 180 degrees, it would probably be over here. And I have a negative and a negative. So negative and negative. And if I went 270, I'd probably be in here. And I've got a positive x value and a negative y value, positive, negative. It works for me. It may or may not be helpful to you. So you want to kind of come up with some way that works for you to try and think about how you're going to remember these. Because some of these can be a little confusing. It's easy to mix them up. So that's my challenge to you.